Hi. So in this video, we'll continue our discussion and move forward on the cost minimization problem. Okay. So in the last episode, we have discussed the profit maximization problem, where the firm can solve this maximization problem by choosing the level of the inputs, right? So where we have the maximization problem by choosing all those y's, right? So those y's are including those possible inputs and outputs. Okay, so we're gonna have this price vector and this y as a vector where we have a constraint where we're gonna have those y within the technology of the product of the firm, right? Okay, so today we're gonna move on and discuss the dual problem to this, and that'll be the cost minimization problem, okay, CMP. So we focus on the single output case for simplicity. So we're gonna again let the z to be a non-negative vector of the inputs, okay, and so the fz will be the production function, which outputs this output, right? So the q will be some certain amount of the output that is required for the production. Okay, why we're gonna need this q is because if you can imagine that you can minimize your costs at as small as you can, but you're gonna have to require yourself to at least to produce something, right? Otherwise, this problem it will be trivial, right? You can just take nothing and produce nothing, right? So there'll be a trivial solution. So, and this q will be the amount of output, and this w will be a vector for a positive vector for the input prices. Okay, so to formalize this problem, that would be this minimization problem. Okay, so where we by choosing this level of the z, okay, so the level of inputs where we're gonna try to minimize this level of the cost here, okay, which is the inner product of w and z. So the only constraint that we have is to, as we said, we have to at least produce something, okay, which is the minimum level for this production, and that'll be the least requirement for this production function, okay, that we're gonna have. So so that's the problem, the CMP, okay. So from this problem, then after we solve this, then either using the first order conditions for the interior solutions or using the general version of the Tucker conditions to solve this problem. So either way, we can have the solution and the value function. So the value function that will be denoted by the C and taking W and Q as the parameters, and the corresponding optimization set of the input. So that would be the solution to this problem that would be denoted by the Z, taking W and Q as the parameters. And it has a long name called conditional factor demand correspondence by the textbook, but that doesn't matter. Okay, good. So next, let's have a look on a picture which help us to illustrate the idea of this problem. Okay, so here, so this red line that would be just below this red line, that would be our production set, capital Y. Okay, so all those areas there, our production set Y. Okay, I'll just write a capital Y here. So remember, where our objective function is to try to minimize the cost. Okay, so the cost will be simply some. So here we just have one input. Okay, so y1 is our input and y2 will be the output. So we only have one price for the input and one input. So that'll be w1 times z1. Okay, and we give some constant number level to this level of the cost. Okay, which is the iso cost line. So then we just move that to the other side. Then we can notice that this is just some straight line that is parallel to the vertical axis, right? So Z1 will be just some number C over some positive number W1. Okay, so intuitively, what we're going to do is to have those vertical lines, okay, which are parallel to the vertical axis. Then we're gonna move those lines as much as we can to the left, okay, to try to minimize. So alternatively or equivalently, that means if you're gonna analyze this problem on the left hand side here in this picture, where we have those y's as negative numbers, okay, then this means we have to move those vertical lines to the right as much as we can. Okay, good. So the constraint that we have is denoted here as this green line. So that'll be our level of the minimum output. That'll be our Q. Okay, and those shaded areas are the levels that we can produce above those minimum level and also within the area of this capital Y within the production technology. Okay, so we can see that there's some minimum requirement for this green level, okay, that is fixed. So the thing that we're gonna do is to shift this blue line as much as we can to the right. But the farthest that we can move is up to here, right? Because we have to hold a minimum level of this Q. If we move further, then this will be some level behind or below this level of the Q, okay? And that will be not satisfying this problem, this constraint. Okay, so this point will be exactly the solution that we're looking for, right? For this input level of Z or this Y1 here. Okay, good. So that will be a example on only one input and one output. Okay, and you can refer to the textbook for another example that they gave for two inputs and one output. Okay, and they're having this on the other figure 5.6.2. But here we are having some example with only one input and one output, and that this is much simpler than their example. Okay, and this is also helpful to further understand this. Good. So the next thing we're gonna do today, that'll be to introduce the proposition or the properties that we have for the value function and the solution to this CMP problem. Okay. All right. So that'll be the proposition 5.c.2. Okay. Suppose that this C WQ is the cost function of a single output technology. Y, okay, with production function F, and Z will be the solution, is the, let's say, just the solution, or the corresponding is the demand correspondence. Okay, it's just for simplicity. So we assume that Y is closed and has the free disposal property. Okay, good. So the first property that we're gonna have is again the homogeneity. Okay, so the value function C is homogeneous of degree 1 in W and non-decreasing in Q. Okay, very straightforward. And the second value function C is concave function in W. Okay. And third, if the sets where we have those Z, where the Fz is at least some output level, if those Z set are convex for every Q, then capital Y minus zq, where w z at least this level of c of wq for all positive vector w. Okay, so here we are having something saying that if the set of all those z's, they're convex, okay, for every level of the q, then we're gonna we can represent our set of technology or our set of production y to be exactly this set, okay, using the level of those costs, which is at least some cost after we solve this problem. Okay, good. So, and you can also verify this this graphically, as we mentioned before, or you can try to prove this mathematically and refer to the textbook for further reading this. Okay, good. So number 4, and z, of course, the solution will be homogeneous of 0 to 0 in W. And 5, if the set z f z at least q is convex, then z itself, this set is convex. Okay. Moreover, if that is strictly convex, then the z is single valued. Okay, we're very familiar with those statements, right? We've seen those a lot of times. Okay, number 6, called Shepard's lemma. So it's saying that it's still something we're familiar. So if saying that if zw bar q consists of a single point, as we just talked about, then the value function c is differentiable with respect to w at this w bar, and the gradient with respect to the w for this c, w bar q, that would be exactly the z w bar q. So the gradient, again, is just a vector of all those partial derivatives of this c, of this value function with respect to all those dimensions. Okay, good. So, and this is also similar to the result that we have in the consumer theory, right? Okay, so that was number 6, and then number 7. Okay, if z is differentiable at w bar, then we further differentiate with respect to w for this z, so that is to differentiate twice with respect to w for the c, w bar q is a symmetric and negative semi-definite matrix with this level, so they differentiate with respect to w of the z w bar q and multiplied by w to be 0. Okay, and 8, and you can always write the number 7 and also the last property we discussed in the last episode, write all those kind of matrix forms in terms of the system of equations, right? If those are helpful for you to understand. Okay, so number 8 is that if F is homogeneous of degree 1. Okay, so F is homogeneous to degree 1 means that it's constant return to scale. Okay, then C function and Z function are homogeneous of degree 1 in Q. Okay, so here this is important that we are looking at Q. Okay, and it's not hard to prove. Okay, number 9. So if we're saying that if F is concave, then C is a convex function of Q. Okay. All right. And in particular, marginal costs are non-decreasing in Q. Okay. And that is in other words. Okay. So up to here, we have introduced all those properties, including the all those homogeneities and convexities and concavities, right? And all those different properties. And you might wonder that why do we need all of those so many properties, right? So, and that is essentially what the economists are doing, right? So people are trying to analyze or to it's not so solving the problem of solving those maximization problems. They're very important, of course, but they are not the most important things in economics, right? So after we solving those problems, then it is also very important to have the interpretations based on the results that we have, right? For example, those those value functions, C functions, and the solutions, those Z functions, right? So, and we're gonna, and this large set of those properties, they give us some implications on something that we can try to learn some ways or some approaches of how to analyze the problems, right? For example, for different parameters, we have different kinds of properties, right? And how do we start to analyze the different properties that we're going to have? For example, the convexities in some parameters and concavities, and which one is the homogeneity in degree of how much, and in terms of which parameters, right? So those are very important features that this problem has, and those are useful sometimes in the explaining some economic environments and some activities, right? Okay, good. So that'll be all for this episode, where we discussed the dual problem to PMP. That'll be the problem of cost maximization. Okay, good.